Today we have the third lecture in supersymmetry. So please go ahead, Professor.
Thank you very much. Okay, this is the lecture. Okay, let me simply summarize what we have done so far. So if you remember what we did last time, basically working with the simplest relativistic theory that you can imagine, describing the free propagation of a boson and a fermion, we managed to find out that this, the action, the Lagrangian of this theory has an extra symmetry, which is, sorry, I don't like this kind of pen. Let's do this. Extra symmetry generated by objects that we call Q alpha and Q bar alpha dot. They are indeed the Weil components of the Majorana spinor, and correspondingly the transformations are described in terms of spinorial parameters. That we call epsilon alpha, epsilon bar alpha dot, in the sense that for a generic field, kind of transformation that we were considering can be written as the action of the operator epsilon alpha q alpha plus epsilon bar alpha dot q bar alpha dot phi. And in the case of scalars and fermions, for the free Lagrangian that we were considering, we found out what was the exact and the precise action of Q and Q bar on the boson and the fermion. Okay. Since are basically the Weil components of the Majorana spinor, what we are considering are generators. Q alpha, remember that alpha is equal to 1 and 2 in the 1/2 zero representation of Lorentz group. And similarly, Q bar alpha dot, still alpha dot is equal to 1 dot and 2 dot, belongs to the 0 1/2 representation. Okay, so what we found in particular is that Q and Q bar satisfy a non-trivial algebra. Because indeed, acting on fields explicitly, we proved that if you consider the anti-commutator of these two spinorial objects, what we find is 2 times P alpha alpha dot. Remember that we will define P alpha alpha dot as sigma mu alpha alpha dot P mu in terms of the 4 component momentum P mu. Okay, moreover, since they belong to 1/2 zero and 0 1/2 representations, they are not inert under Lorentz, so they transform non-trivially under Lorentz transformations. Okay, therefore, if we collect everything together, we can eventually write an algebra for generators, which include these new generators QQ bar, that from now on will be called supercharges or supersymmetry generators, plus generators of Lorentz and generators of Poincare translation. So in total, basically Poincare. So what we can do is to write, so collecting everything together, we eventually find the following set of non-trivial commutator and anti-commutator that I will write explicitly, because this will be our main subject, our main topic for today, studying basically this algebra. So we have, first of all, what we have already written, Q alpha and Q bar alpha dot. When they anti-commute, they provide you with P alpha alpha dot. As I said, the Q and Q bar transform under Lorentz, which means that when I consider the commutator of the generic Lorentz generator mu nu acting on Q alpha, this is equal to minus 1/2 sigma mu nu alpha beta Q beta. And similarly, I will tell you in a moment what sigma mu nu is. Let me first of all write down all the commutation relations. This is 1/2 Q bar beta dot sigma bar mu nu beta dot. I should put alpha dot up here. Okay. And then you have the usual Poincaré algebra. So P nu is equal to 0. Then we have a non-trivial action of mu nu over P rho. This is I eta nu rho P mu minus eta mu rho P mu. And finally, if I commute to Lorentz generators, what we get is I times eta mu rho m mu sigma minus eta mu rho m mu sigma plus eta mu sigma m mu rho minus eta mu sigma m mu rho. I hope I did not mess up things. Okay, this should be okay. And this is the algebra, which is consistent in the sense that it satisfies the Jacobi identities, the great Jacobi identities, because now we have also anti-commutators into the game. The first obvious observation is that, differently from what was happening in the ordinary case when we consider a theory invariant under Poincaré plus internal ordinary group symmetries, this time we have that Q and Q bar talk non-trivially with the Poincaré generators, because as I said, they transform non-trivially under Lorentz transformations. Okay. The set of commutator and anti-commutators that I wrote down is what we call n = 1 supersymmetry algebra. Okay. Why I said that this is our main character today, because now what I'm going to do is, first of all, try to understand how many physical properties I can grasp concerning, particles which transform in a particular way under the action of these generators, properties that I can infer directly from the algebra itself. And second, very important, what we will look at is how to build up representations of supersymmetry algebra, and in particular, how to organize particles into supersymmetry representations. Okay, this is basically the content of my today lecture. Okay, so I should start with the kind of easy observations about this algebra. So first of all, let me call this set of transformations 1. The first observation is that, of course, as I said already in words, this is a great algebra. So let me say observations. The first observation is that 1 is a great algebra. In fact, we can assign sort of parity. We can assign parity equal to 1 to even generators and parity equal to -1 to odd generators. Okay, and you will see that the set of commutation and unline commutation relations that I wrote here are consistent with this parity assignment if we identify even generators with P mu and mu nu, whereas we identify with odd generators Q alpha and Q bar alpha dot. In fact, what happens, consistently with what we wrote above, is that now we have that if you commute two even generators, you obtain an even generator. If you commute an even generator with an odd generator, you obtain an odd generator. Fine, and this is consistent with the parity conservation on the left and right side of these identities. And finally, if you anti-commute to odd generators, you get even. Fine. Okay. The second important observation is that because of the nature of Q and Q bar, remember Q and Q bar are the entries of the Majorana spinor. Therefore, in our set of conventions, Q bar is nothing but the complex conjugate of Q, okay? Therefore, the algebra that I wrote down above has an extra U1 symmetry, okay, which acts on Q and Q bar. So it acts directly on the supercharges, and it acts this way. So if you look at the algebra above, you will realize that it is invariant if we transform Q alpha into e to the I beta Q alpha, and Q bar alpha dot into e to the minus I beta Q bar alpha dot, where beta is any real number constant. Okay, this is easy to see because the only generators, sorry, the only commutation relation which contains Q and Q bar are these ones, and you see that Q bar on the left-hand side here will produce a phase which cancel, whereas on the left and right-hand side we do not have any phase, and the same here, we have a phase emerging on the left-hand side, but the same phase arises on the right-hand side. Okay, so this is trivially invariant under this U1 set of transformations. Therefore, we can define a U1 R generator, which acts this way. With respect to this generator, you see kind of the transformation that I wrote here. Q alpha has charge 1 and Q bar has charge -1. So we can write that R Q alpha will be equal to Q alpha. R Q bar alpha dot will be equal to minus Q bar alpha dot. And of course, the rest of generators, in particular the even sector of generators, are neutral with respect to R, so they do not transform. Okay, the generator R, which corresponds to this U1 symmetry, is called generator of R symmetry. Okay, so remember, when you talk about R symmetry, you mean transformation of supersymmetry generators, Q and Q bar. Okay, so let's see, first of all, what kind of general informations we can infer from algebra 1 concerning particles which somehow transform under the action of these generators, or if you wish, particles described by a theory by Lagrangian, which is invariant under the action of N=1 supersymmetry generators. Okay, so general, let's say, general physical properties that can be inferred from algebra 1. Okay, in particular, let's say the news in this algebra is the first anti-commutator. Sorry, this one. Okay, this is kind of new thing. So let's focus on this anti-commutator and see what happens. Okay, so we consider, I will never learn to do that. Consider Q alpha, Q bar alpha dot equal to 2P alpha alpha dot. Remember that P alpha alpha dot, as I said, is defined this way. Okay, if you use the properties of the sigma mu matrices that we listed at the very beginning of the course, you can sort of invert this relation. And from here, you can write that P mu is equal to 1/4 sigma bar mu alpha dot alpha Q alpha Q bar alpha dot. Okay, but remember that if we are dealing with a set of particles, P mu is the generator of translations, and P mu corresponds to the vector momentum of the particle. So this is the object that I'm going to consider, which comes directly from the algebra. In particular, what I want to consider is the energy. Let's suppose that P mu describes the force momentum of a particle. You know that the zero component corresponds to the energy. Let me call it H. So by definition, this is 1/4 sigma bar 0 alpha dot alpha Q alpha Q bar alpha dot. Okay. However, we know that sigma bar 0 is the identity. So this is the identity, the way we define the identity. But the identity has only non-vanishing components, the components 1.1 and 2.2, and they are equal to 1, okay? So this is nothing but 1/4. Let me write this way. Q1, Q bar 1 dot plus Q2, Q bar 2 dot. Okay. This is the energy operator. What do we want to do with this energy operator? Let's consider a generic state of my theory. A generic state, let me call it A, which is, you know, we are dealing with the ordinary quantum field theory. So the state A, it has to be thought as a state, an excited state created by the action of some field, the creation part of the field acting on the vacuum of the theory, okay? So generically, let's call it A. I want to see, for instance, which is the energy of the state A. Therefore, what I have to compute is this quantity, okay? But by computing this quantity, I can express H as we wrote it here. Okay. Therefore, this is equal to 1/4 A Q1 Q bar 1 dot plus Q2 Q bar 2 dot A. You can do the calculation. This is one line calculation. You simply write the anti-commutator explicitly as Q bar plus Q bar Q, and you will immediately realize that this is nothing but 1/4 the norm of the state Q bar 1 dot A square plus the norm of the state Q1 A square plus norm Q bar 2 dot A square plus the norm of Q2A square. I hope this is easy for you to understand. Still, because Q bar is the complex conjugate of Q. Okay. This is a very interesting result because, you know, what we find is that the energy is the sum of non-negative quantities. So what we can conclude is that the energy for any generic state A, belonging to, you know, supersymmetric theory, is always greater or equal to 0. Cannot be negative. Okay. But remember that the energy, the total energy, will be the sum of the kinetic energy plus the potential energy. The kinetic energy, by definition, is always positive. Therefore, what we conclude is that in a supersymmetric theory, the potential energy is always positive or at most 0 for any generic state A. Okay, so this is the first important, as I said, non-trivial physical property of the supersymmetric theory, describing particles affected by supersymmetry, that we can simply infer from the algebra. We simply used the anti-commutator. In particular, if we consider the vacuum state, okay, what happens if we compute the energy of the vacuum state? Let me call it E0. Okay, you basically redo the same, exactly the same calculation, but you have to substitute A with the vacuum. And of course, what you can conclude is that if supersymmetry is preserved at quantum level, which means that there is no spontaneous supersymmetry breaking, which means that the vacuum is supersymmetric invariant. If there is no spontaneous SUSY breaking, which means that, you know, the action of Q on the vacuum and Q bar on the vacuum has to be 0. The vacuum is invariant, is SUSY invariant. Then, simply looking at the previous calculation, when you replace A with the vacuum, you will find that the energy of the vacuum is 0. And you can even realize, putting all this information together, that this is basically a necessary and sufficient condition for having supersymmetry preserved at quantum level. So if your quantum theory preserves supersymmetry, then the energy of the vacuum state is necessarily 0. from the previous analysis, what we find is that for any other, as we found here, for any other state which is not the vacuum, the energy will be positive. Okay. Okay, so the situation is the following. Basically, what the conclusion that we can draw. Conclusion for a supersymmetry theory. The potential energy has to be of the form. Let me simply draw the behavior. If we plot the potential energy as a function of the fields of the theory, of course, the vacuum state where there are no fields will have energy 0, and for any other excited state, you have potential energy positive. This is a very important observation because we now have basically a criterion to investigate whether supersymmetry is preserved at quantum level or not. In fact, if the theory exhibits spontaneous SUSY breaking, which means that the vacuum state is no longer killed by Q and Q bar, then the potential energy has to be this form, has to be positive as usual, but the minimum of the potential energy is no longer 0. Okay, so you have a criterion to understand whether there is a spontaneous symmetry breaking. Just draw the potential energy of your theory and check whether the minimum of the potential is 0. In this case, supersymmetry is not broken, or different from 0. In this case, supersymmetry is broken. Okay, so this is a kind of similar thing that happens already when you have ordinary spontaneous symmetry breaking of internal symmetries. In fact, remember for ordinary theory, for ordinary internal symmetries, no spontaneous symmetry breaking means, again, that the potential has a single minimum, can be whatever you want, but has to be a single minimum, whereas spontaneous symmetry breaking is realized when you have the general vacuum. Okay, if you fix this vacuum, of course, you break. This is the famous Mexican hat. Okay, so as I said, for supersymmetry, the criterion is energy, minimum energy equal to 0, or minimum of the energy not equal to 0. Okay, this is the first important thing that we can infer from the algebra. The second thing that I would like to mention still relies on this relation that I wrote here, that the energy is always positive or at most 0. Now we learn that the 0 energy is realized in the vacuum state. For excited state, we will have a positive energy. Okay, so as I said, let me say it again, for vacuum state, we have energy equal to 0. Excited states A have energy strictly positive. But if the energy is strictly positive, it means, let me go up to the calculation that we did here. Here. If the energy is strictly positive, it means that when you act with Q or Q bar on the excited state, some of these terms have to be non-vanishing. Okay, therefore it means that the action of Q or Q bar on the excited state is non-trivial. So from here, I can conclude that it means that Q, when I write Q, is just Q, and forget about alpha. So this has to be different from 0, and or Q bar has to be different from 0. Okay, but that means that if Q, let's consider for instance Q, if Q acting on A is different from 0, it means that when I act with Q on A, I will get a new state, A prime. Correct? But remember that I told you that Q, in particular Q alpha, are the two components of a bispinor. So Q carries spin 1/2, and therefore, with the usual rule of combining, summing up angular momenta, you will of course find that if you start with a spinor, sorry, not even spinor, with a state which has some spin S, then let me call it S A, we will find that S of A prime will be S A plus or minus 1/2. So you are going to change the spin of your state by a quantity 1/2, okay? Which means, of course, that if the original spin S of A is an integer, so we are dealing with bosons, what you will get when you apply Q to A is a fermion and vice versa. And this is something that we already noticed last time, that in fact acting with Q, we will transform bosons into fermions or fermions into bosons. Okay, very good. This is something that we already mentioned last time, but let me go through it again. Remember that we have a Casimir operator, which is still P square, because P square commutes also with the new generators Q and Q bar. Okay, therefore, what we can say is that the boson and the fermion related by the SUSY transformation will have the same mass. Remember that P square has eigenvalues that we recognize as the mass of the particles. Okay. Therefore, if I transform boson into fermion, if we start with a boson which has mass m, the corresponding fermion will have a mass m. And in fact, and vice versa, of course, if we start with fermion, we will generate a boson with the same mass. And in fact, these are the pair of particles, the generating mass that in principle, if supersymmetry is realized, we should observe in nature. So as I said the last time already, to each boson, there is a corresponding super partner, which is a fermion, but which has the same mass. And to each fermion corresponds a new particle, which is a boson, the corresponding super partner with the same mass. Okay, good. Same mass. Okay, let's go more carefully through, sorry, but let me mention something more. This is not the end of the story. Not only P square commutes with Q and Q bar, but if you go back to the supersymmetry algebra that you wrote at the beginning, you will see that, so in addition, we have that all the components of P commute with Q and Q bar. Okay, therefore, not only the mass is conserved when you apply a supersymmetry transformation, but also P mu, all the four components of P get preserved. All the components of P mu are preserved. Therefore, what I can say is that if I have a boson which transforms into a fermion, as I said, the same if I have a fermion which transforms into a boson, they will have the same mass, but they will also have the same energy, and they will also have, of course, the same momentum. Okay. So I can start playing with Q. So I can, at this point, I can start doing sort of nice game. So what I can do is, let's suppose we start with a boson state, bosonic state. Let me call it B, with a given mass, a given momentum, a given energy. Okay, so what is the operation that I can do to generate the super partner? As I said, what I can do is to apply, for instance, Q1 to B, and also Q2 to B. I will obtain, let me call it F1 and F2, which are the two components of the spinor, okay? Therefore describing the fermion. This is, let's say, the first step number 1. I'm wondering whether I can keep going, applying Q and see what happens. The answer is yes, I can apply, of course. Now you take F1, for instance, let's consider this one. I can consider applying Q2 to F1, because this is equal to Q2, Q1, B, correct? The same for F2. Of course, I can apply Q1 this time to F2, because this is Q1, Q2, B. Great. But I cannot keep applying the same Q. If I insist in applying Q1 to F1, I will get 0, because this is proportional to Q1 square B, and this is 0, because Q1 square is 0. Remember that QQ is equal to 0. And the same, if I insist in applying Q2 to F2, I will get 0. Okay. Therefore, okay, this is what I can do. Therefore, I'm going to ask myself if there are any other extra operation that I can do. Of course, at this point, starting from, let me give a name to this new, let me call this B tilde 1 and B tilde 2. I'm wondering whether I can still apply some Q1 or Q2 to B tilde 1 and B tilde 2? What do you think? Of course, at this point, no, I'm killed. Because, you know, because Q1, let's say in general, Q, whatever you do, Q cube is equal to 0, because Q cube means to have at least a Q1 square or a Q2 square, which are 0. So you cannot longer go higher with with your chain of Q. You're stopped at this level. However, what I can do, well, let's consider still step 3. What I can do at this point is to apply some Q bar. I could apply Q bar 1 dot or 2 dot to B tilde 1 or 2. And this is in fact something that I can do. This is not 0. Okay. Then I can certainly go higher 1 step. I can certainly apply Q bar 1 dot, Q bar 2 dot to B tilde 1 or B tilde 2. This is still non-zero. But at this point, I have to stop, because if I keep applying Q bar, I will generate Q bar cube, which is 0. So now I have to stop. Otherwise, I will generate Q bar cube, which is 0. Okay, so what I realize is that if I start with a generic state, we started with a bosonic state, but you could even start with a fermionic state. It is the same thing. If we start with a generic state, we can build up a chain of states which will differ from the original state in spin, of course. Every time you apply a Q or Q bar, you increase or decrease the spin by 1/2. So you always move from boson to fermion to boson and then to fermion, okay? But the change, this change of fields is made up by a finite number of fields, because at a certain point, I cannot keep applying Q and Q bar because I get 0, okay? So the finite number of states that we generate from the original state B, of course, or F, you can do the same, as I said, starting with the fermion. The final number of states that we generate from the original state B, it's important that it is finite number, is called a SUSY supermultiplet. Okay. And of course, this supermultiplet contains, among this finite number of states, some states which are bosons and some states which are fermions. Okay, because as I show you here, of course, when you start applying 1Q to the boson, you produce a fermion. When you start applying 2Q to the boson, which means a Q to this fermionic state, you get a boson. When you apply another Q bar to this boson, you will get a fermion, and so on and so forth. Okay, so what you get here is that this finite number of states, this supermultiplet, contains a given number of bosonic states and a given number of fermionic states. A supermultiplet is always made by bosonic and fermionic states. What I want to show you is that exploiting, again, only properties of the supersymmetry algebra that we wrote at the beginning, we can already infer how many bosonic and how many fermionic states a supermultiplet contains. Okay, so this is what I will be trying to answer. So the question is, how many bosonic and how many fermionic states in a multiplet? I can answer this question without making any reference to the particular multiplet that I am considering, but just, as I said, just exploiting properties of the supersymmetry algebra. How do I proceed? In order to answer this question, we introduce the fermionic number operator. Which is defined in this way. I mean, the operator is simply -1 power f, where if I apply -1 power f to a boson, I get the boson. If I apply -1 power f to a fermionic state, I get minus the fermionic state. So basically, f is equal to 0 for bosons and f is equal to 1 for fermions. Okay, this is the definition of the fermionic number operator. You can easily prove that the fermionic number operator, actually, I prefer to call it fermion number operator. The fermion number operator always anti-commute with Q and Q bar. So the two identities that's very easy to prove are the following. If you anti-commute the fermion number operator with Q alpha, you get 0. And similarly, if you anti-commute with Q bar alpha dot, you get 0. You can prove these two identities by applying the anti-commutator on the left-hand side to a bosonic state or to a fermionic state, and you will always get 0. Okay. Now let's consider again the energy that I wrote before. Remember? Well, I can rewrite it. Consider again the energy operator, which by definition is P0, that we found to be equal to 1/4 Q1 Q bar 1 anti-commutator plus Q2 Q bar 2 dot. Okay. And compute the trace of H on a supermultiplet made up by some set of states, I from 1 to some number. Okay, so I have a supermultiplet. As I told you, it is for sure made up by a finite number of states. Let me call these states I, labeled by an index I. Okay, what is the definition of, sorry, I want to compute the trace, not actually of H, but -1 power f H. Okay, so if I compute the trace of -1 power f H, we can compute it in two different ways. well, in one direction, I'm going to use the definition of trace on a set of on a multiple, so in a set of states. So this will be given by the sum over I minus 1 power f h I. This is the standard definition. Whereas in the other direction, I will rewrite the trace as the trace of minus 1 power f times 1/4 Q1 Q bar 1 dot plus Q2 Q bar 2 dot. Okay. Okay, so if you move in the right direction, so you concentrate on this definition of the trace, you immediately realize the following. First of all, remember that all the states of a multiplet, this is something that I told you, they all have the same energy. So I can rewrite this as, you know, the common energy that they have. This state, the action of H on the state can be written as the common energy of the multiplet times I. And this is just an eigenvalue that I can move out. So this will be equal to the energy times the sum of I minus 1 power f I, correct? However, minus 1 power f will be 1 when I is bosonic state, and it will be minus 1 when I is fermionic state. So here I can write that this is nothing but the common energy to the multiplet times the number of bosons minus the number of fermions. Okay. Therefore, what I have found so far is that, okay, apart from this E overall, the number of bosons minus the number of fermions inside a supermultiplet equals what I can read from this other identity, this one, okay? So this is equal to 1/4 the trace of minus 1 power f Q1 Q bar 1 dot plus 1/4 the trace of minus 1 power f Q2 Q bar 2 dot. Very good. We have more or less done, because now you have to take into account, well, first of all, you write the two anti-commutators explicitly as QQ bar plus Q bar Q. Then you use the cyclicity of the trace to move around Q and Q bar. And at the end, you will also use the observation that we made above, which means that the fact that the Q and Q bar anti-commute with minus 1 power f. If you do that, what you will find is that this quantity and this quantity is equal to 0. You can do it easily using cyclicity of the trace and what we found earlier, the fact that minus 1 power f commutes with Q, anti-commutes with Q and Q bar. Still, something that I can infer only from the algebraic properties of these super generators. Therefore, what I can conclude, this is another very important physical consequence, that if I build up a supermultiplet made up by a set of states, the number of bosonic states and the number of fermionic states in a supermultiplet is always equal, okay? So what we can conclude that in a supermultiplet, the number of bosons equals the number of fermions. And this is another very important statement. Okay, at this point, what time is it? Well, I don't know, maybe this time we can have a break now, because okay, so what we can do now, as I said, is to go through the construction of supersymmetry, of the representations of supersymmetry algebra. And basically what I want to discuss and show you is that this set of finite number of fields that I call supermultiplets are nothing but associated to representations of supersymmetry algebra. Okay, so let's go to this new chapter, representations of SUSY algebra. Okay, so what we can do, I lost my notes, here it is, well, what we have to do indeed is to split the discussion between massive representations and massless representations. Typically, in all the books and reviews, whatever you find, first the discussion about massless representations, because this is a little bit easier, and then the massive representations, well, for some reason, I like to do the opposite. So we will start with massive representations, okay? Let's consider it means that I'm going to consider massive particles. We know that massive particles carrying spin s can be described by a state that we can label this way: the mass, the spin, and the projection of the spin along one of the three directions. Let me call this S3, okay? Remember that S3 can take values between minus S plus 1 up to S, which are 2S plus 1 values. Okay. In particular, I want to study how, given a spectrum of massive particles this way, they can be reorganized in terms of representations of the supersymmetry algebra. To do that, we better go to what we call the rest frame. So it is convenient to go to the rest frame of the particle, rest frame where the mu is M0, 0, 0, of course. Therefore, remember, from here, what I can write is that if I take the supersymmetry algebra, QQ bar, remember this is twice P alpha alpha dot, which is twice sigma mu alpha alpha dot P mu. If you insert this particular choice for P mu, the only surviving term will be P0, which is nothing but M. So you will get 2M times what? Sigma 0, but sigma 0 we said already is the identity. Okay. Which means that what I find here is that Q1, Q bar 1 dot is equal to 2M, and Q2, Q bar 2 dot is equal to 2M. It's the same. Whereas if I commute, anti-commute Q1 with Q bar 2 dot or 2 with 1 dot, I get 0. Okay, so basically what I find is a set of two disjoint algebras of let me first of all of operators. And if you simply rescale, so if we rescale Q and Q bar by 1 over square root of 2M, so we define a small Q1 given by 1 over square root of 2M, Q1, and so on and so forth for the others. In terms of these rescaled generators, what we have is Q1, Q bar 1 dot equal to 1, and Q2, small q, 2, Q bar 2 dot equal to 1. Okay, so what we have found is basically that from the supersymmetry algebra, we obtain, in the massive case, two independent Clifford algebras. Dependent Clifford algebras, which are typically the algebras of anti-commuting operators, which can be identified with creation and annihilation operators. Okay. Therefore, what I can do is to start, well, first of all, you should check from the algebra that in fact, Q1 and Q2 can be identified with let's say annihilation operators in terms of angular momentum, whereas Q1 dot and Q bar 2 dot can be identified with creation operators in terms of angular momentum. This is simply what happens if you consider the commutator of mu, in particular M12, which is the third component of the angular momentum with Q1 and Q bar 1 and Q2 and Q bar 2. In any case, what I can do here is to now generate a representation of these two independent Clifford algebras, as we usually do when we have the algebra of creation and annihilation operators. So this is algebras of creation and annihilation operators. Okay, since they are anti-commuting, as usual, let me stress this point because this is important. Let me do it here. Remember that Q1 square is equal to 0 and Q2 square is equal to 0, or this comes from, of course, the original. And similarly for Q bar. Okay, so how do I construct a representation? First of all, in order to construct a representation, a given representation of these two algebras, which, as I said, are equivalent to the SUSY algebra. So what I'm going to do is to construct representations of the supersymmetry algebra. We define a Clifford vacuum, which is defined, let me call it S. Well, let me call it actually, as I called it already earlier, M, S, and S3, okay? This is for sure a state in a given representation of Poincaré. Representation of Poincaré algebra. So it carries mass, it carries spin, but being the Clifford vacuum of these two algebras, it means that it is defined by the conditions that Q1 over this state is equal to 0, and Q2 on this state is equal to 0. This is the definition of Clifford vacuum. At this point, starting from this initial state, I can build up the whole representation by acting with creation operators, which are, in our case, Q bar 1 dot and Q2, Q bar 2 dot. Okay, therefore, we can consider the following table. Let me call, so we have the state here, spin, and the number of components. Okay, so we start with this particular state that we picked up in our Hilbert space. The spin is S, and of course, originally the number of states is 2S plus 1 because we have 2S plus 1 possible projections of the spin. Good. At this point, I can act with Q bar, one of the two, Q bar alpha dot. Let's stick to Q bar alpha dot, could be Q bar 1 dot or 2 dot, apply to this state, which is the spin. I told you already that these operators carry spin 1/2. So when you act with the operator on a state which has a spin S, you have to rely on the general theory of, summation of angular momentum. And what you will get are states which can have spin S plus 1/2 or S minus 1/2. Okay. In the first case, the number of states will be twice S plus 1/2 plus 1. In the second case, it will be twice S minus 1/2 plus 1, assuming that S is bigger than 1/2. In total, we have 2 times 2S plus 1. Okay. Then I can move on. What I can do is to apply another Q bar. Okay, let's see what happens. I can apply Q bar beta dot to the previous state. Okay, however, if you remember the famous Fields identities that I wrote at the very beginning of the course, this Q bar beta dot, Q bar alpha dot can be written as, so this is proportional to epsilon alpha dot beta dot Q bar square applied to MS3, where Q bar square means Q bar alpha dot contracted with Q bar alpha dot, but Q bar square at this point is a scalar. Okay, therefore, we are back to spin S, because now we are applying a scalar, a Lorentz scalar with spin 0 to a state which has spin S. So still we have 2s+1 components. Okay. I should stop here at this point. I have to stop here, in fact. Why? You could always tell me, okay, you cannot apply another Q bar. True, because otherwise I would get a Q bar cube, which is 0. But in principle, I could apply Q, because now Q is no longer acting on the vacuum, and therefore something nice could happen. So now note that if we apply some Q, we do not obtain an independent set of states. Why? In fact, suppose, for instance, I decide to apply Q gamma to this state that I was considering here as the last state of my chain. So I will apply Q gamma to epsilon alpha dot beta dot Q bar square M S S3. Forget about the epsilon. It does not play any role at this point. Since Q kills this, remember, this is the Clifford vacuum, so Q kills this state, I can always rewrite this expression as the commutator of Q with Q bar square. Because, you know, if you expand the commutator, you will be back to this term minus Q bar square Q, which is 0. Okay. However, if you use the algebra, using the algebra, this term is proportional. Proportional means up to some sign or some factor. The important point is that this is proportional to something like Q bar, let me call it gamma dot, D, where this is the derivative, gamma dot of P. Let me call it, we will keep playing with P. This is P gamma dot applied to S3. Therefore, you see, up to the action of the momentum, which will give you the eigenvalues corresponding to the momentum of the particle, you are back to a state like this one. Okay, so we no longer obtain any new independent state. Okay, starting from this observation, I can conclude that the set of 3 steps that I realize here completes the construction of this representation generated by this Clifford algebra. Sorry, it's Clifford vacuum. Okay. The interesting thing is that in addition to what I already mentioned here, what we can say is that this set of states is closed because basically of what I was mentioning here. This set of 3 states, it's not really 3 because, you know, we have many states here. Now, in a moment, we are going to compute how many. But let's say the set of states that you find in these 3 steps closes under, there is a question, I'm coming to your question, closes under the action of the supersymmetry algebra, in the sense that the set of states that I'm building up in this chain will transform one into the other under the action of supersymmetry generators. Okay, that's why we claim that the set of these states build up a representation of supersymmetry algebra. So let me conclude before answering the question. So the conclusion is that if I consider M S S3 together with the Q bar alpha dot, M S S3 together with Q bar square, M S S3. Okay, this is a representation of SUSY algebra corresponding to mass M. Remember that all the multiplet belonging to a given supermultiplet have the same mass. So this is a representation of SUSY algebra mass M and spin of the lowest component equal to S. Okay, so sorry, there are a lot of questions. So what about the Q1 bar, Q2 bar? Yes, this is what I was doing here. This is included in what I was doing here. If you apply Q1 bar dot, Q2 bar dot, you can rewrite this as epsilon 1 dot 2 dot Q bar square because of the field's identity, and this is a scalar. Okay. I can even argue this in a different way. If you consider Q bar square, by definition, this is Q bar alpha dot, remember, which is Q bar 1 dot, Q bar 1 dot, plus Q bar 2 dot, Q bar 2 dot. But if I move 1 dot and 2 dot down, remember I can do it using the epsilon tensor. This will be plus or minus Q bar 1 dot, Q bar 2 dot, minus Q bar 2 dot, Q bar 1 dot, because the epsilon tensor give you the sign, and this is eventually what you want to apply, Q1 bar, sorry, Q bar 1 dot, Q bar 2 dot. So what I'm basically saying is that Q bar 1 dot, Q bar 2 dot is nothing but Q bar square, so it is a scalar. Okay. Yeah, now let me go to, now let me apply. Now I don't know what was here, sum. Okay, another question. Vanishes because they anti-commute, yes. And Q1, yes. In that case, we are not acting over the vacuum. In which case? This case, I think you are referring to this. Yeah, I guess so. Yeah, in this case, we are not acting on directly on the vacuum, on the Clifford vacuum. Therefore, I do not expect this to be 0. And in fact, it is not. But what I can do is exploiting the fact that this is the Clifford vacuum. I can rewrite the expression in terms of the commutator. And therefore, you know, this is a typical thing that happens in supersymmetry algebra. When you start applying many Qs, either you get directly 0, or you can always trade your long list of Qs in terms of a smaller number of Qs times some momentum, because we are basically exploiting the Q bar equal to P identity from the algebra, from the original algebra. And this is in fact what I was doing here. You see, I start with 3Q, which is not 0 to begin with, and I can trade it with 1Q and 1P. This is typically what you do when you do not get trivially 0. Okay. Okay, so basically what I claim here is that this is a representation, but as you can imagine, I mean, as you can understand, easily from what we, I mean, comparing what we are doing now with what we have done before the break, this thing, I mean, this set of states that I build up here and that I claim, which I claim to be a representation, nothing but the supermultiplet. This is just a supermultiplet that I was considering before. Okay, so supermultiplets are nothing but representations of SUSY algebra. Okay, so this is a supermultiplet. Okay. I can give you some relevant example at this point. Yes, because these are important in physical, in, let's say, sort of physical theories. So relevant examples of massive representations. The first relevant example is the massive chiral. Well, actually anti-chiral in this case. Multiplet or representation. Which is obtained when we set s equal to 0. This corresponds to s equal to 0. So in the previous table, we simply set s equal to 0. So what you find, well, let's rewrite, but let me first of all mention things here. You will start with the, the lowest spin state, which is 0. Then when you apply 1 q bar, is s is equal to 0, you will simply get a new state with spin 1/2. And when you apply 2 q's bar, you are back to spin 0, okay? And the number of components in this case, of course, they become kind of trivial because s is equal to 0. So in this case, my table, state, spin, and the number of components becomes, the state is still m0, 0, spin 0, and we have one component. Then when we apply q bar alpha dot, we get spin 1/2, and we have 2 components. And finally, when we apply q bar square, we are back to spin 0, and we have 1 component. Okay. Another relevant multiplet or representation that we can define is the one which corresponds to spin 1/2. This is the massive vector multiplet or representation corresponding to s equal to 1/2. So in this case, state, spin, number of components. Okay, let me go back to the general construction. If now you set s equal to 1/2 to begin with, you will obtain, as the second step, a particle with spin 1/2 per 1/2, and a particle with spin 0. And finally, at the third step, when you have, you are applying q bar square, you are back to spin 1/2. Okay, so let's see what happens also in terms of the number of states. So in this case, we have the state, which is, okay, state I could avoid writing one. So this is m. Let me just call it 1/2, okay? M is always the same, so we have a spin 1/2, and therefore we have 2s plus 1 components, which in case is 2. Then I apply q bar alpha dot to 1/2. And in this case, what I will get, as I said, I obtain a spin 1 particle, which has 3 components, and a spin 0 particle, which has 1 component. And finally, when I apply Q bar square, I am back to spin 1/2 with 2 components. Finally, a third relevant multiplet, which is worth mentioning, is the one corresponding to spin 3/2. This is the massive Weil multiplet. If you set S equal to 3/2, state spin number of components. So the state now is 3/2. It has a spin 3/2, and to begin with, it has 4 components. When we apply Q bar alpha dot on 3/2, okay, now we obtain, as remember, S plus 1/2, which means spin 2, and S minus 1/2, which means spin 1. If we have spin 2, we have 5 components. If we have spin 1, we have 3 components. And finally, if I apply Q bar square to 3/2, we will be back to spin 3/2 with 4 components. Okay. Let's first of all compute the dimension. What we call the dimension of the representation is basically the number of components that may build up the representation. Let's see what happens if we compute the dimension of this massive chiral multiplet. The dimension is made by, you see, we have 1 plus 1, 2 bosonic components plus 2 fermionic. So 2 bosons plus 2 fermions, which is equal to 4. And we start testing that, in fact, this representation is made by the same number of bosonic and fermionic states. Let's see if this happens also for the others. Let's compute the dimension. The dimension of this other representation. In this case, we have 3 plus 1 here, which means 4 bosonic components, plus 2 plus 2, which is still 4 fermionic components. So the dimension in this case is 8, but still coming from the same number of bosonic and fermionic components. And finally, let's see what happens here. Here we have the bosonic states are these ones. So we have 5 plus 3, 8 bosonic states, plus 4 plus 4, 8 fermionic states. So the dimension is 16, but still made by half bosons and half fermions. You can easily compute, indeed, the dimension of the generic representation that we built up here, because the dimension here is nothing but the number of 2s plus 1 projections times 2 plus 1 plus 1. So this is equal to 4 2s plus 1, which I would prefer to write as 2 power 2 2s plus 1. This is the generic dimension of the massive representation in n equal to 1 superalgebra. Okay. Okay. Yeah, we still have time. Now, what I would like to do is, of course, to move to the massless case, unless there is a question. Does this mean that to get a spin 2 particle in a SUSY theory, we also need to get not only 2s spin 3 alpha, but also a new spin 1 boson? Yes, this is it, indeed. Spin 2 particle means the graviton. In fact, this is basically the content of supergravity, and equal 1 supergravity. I don't want to go into because we do not have time, of course, to mention anything about supergravity, but when you construct the graviton multiplet, of course, it comes with a number of superpartners, which include spin 3 up, which is the gravitino, and spin 1 bosons, yes, which are vector fields, indeed. But this is still massive, so to really get to supergravity, we should go to the massless representations that I'm going to do now. Okay, so I don't see any other question, and so I assume I can go on. Okay, massless representations. Okay, so what I want to do now is to start with the state which describes a massless particle. Remember, for a massless particle, p squared is equal to 0. Therefore, I cannot go to the rest frame, but what I can do is to go, we choose what people call the standard frame. Okay, maybe I should turn my light to see my face in this way. Okay, the standard frame is P mu given by E0, 0, E, where E is the energy of the particle. Okay, so if I use this P mu, let's see what happens in this case when I compute the anti-commutator of QQ bar. Remember, this is twice sigma mu alpha alpha dot P mu. Okay, this time I have two components of P mu, non-vanishing components. So this is twice E, and E appears together with sigma 0 and sigma 3 alpha alpha dot. Okay, but remember sigma 0 is the identity, sigma 3 is sigma 3. So what you get here is the matrix 2, 0, 0, 0, which has as the only non-vanishing component the entry 1, 1 dot. Okay. Therefore, this time, that's why people typically do massless case first, because it can to be easier. Therefore, this time what we get is that Q1 Q bar 1 dot is equal to 4E, whereas Q2 Q bar 2 dot is equal to 0. Okay, and as usual, if you compute Q1 Q bar 2 dot or 2 1 dot, this is 0. So we do get one single independent Clifford algebra, whereas Q and Q bar, this time they anti-commute. So, okay. Therefore, it means that this time, basically, we have half of the Clifford algebras compared to the massive case. So reconstructions should be sort of easier. In particular, you can proceed as we did above. So we rescale the Q's, writing Q1 as 1 over the 2 square root of E, Q1, and the same for Q bar. Q bar 1 dot. Therefore, what you obtain is the usual Clifford algebra for creation and annihilation operators. Okay, whereas the second Clifford algebra this time is trivial. Okay, now how do we label states in massless states? Remember, for massless particles, we introduce quantum numbers that are the energy that we define already here and the helicity. Okay, so massless states are labeled as E lambda, where E, as I said, is the energy and lambda is the helicity, which is nothing but the eigenvalue of the helicity operator. The helicity operator, you should know, helicity basically measures the projection of the spin along the direction of motion. So up to a normalization, this is nothing but L dot P. Well, L is the angular momentum. In terms of, so vector L is L1, L2, L3, which is M23, M31, M23, M12. Okay, therefore, if you remember the way we define the Pauli-Lubansky vector, basically what you get is that W, let me write this way, gamma is nothing but 1 over E W0, the zero component of the Pauli-Lubansky vector. Good. Therefore, you can even trade the helicity with the eigenvalues for W0. Okay, therefore, what I can say is that I will consider these E lambda states as eigenvectors for the energy operator plus the W0 operator. So W0, when acts on this state, gives me exactly E lambda. Okay, I'm telling you that because now I want still to recognize in this non-trivial algebra Q1 and Q bar 1 dot as being well, actually annihilation and creation operators respectively. So what I'm claiming is that Q1, let's consider the big Q, Q1 is a lowering helicity operator, whereas Q bar 1 dot is a raising helicity operator. In fact, still from the algebra, the original algebra 1, we can we can show that if you commute W0 with the Q1, what we get is minus E over 2 sigma 3 1 1 Q1, and sigma 3 1 1 is simply 1. Okay, so this is simply equal to Q1, whereas W0 with the Q bar 1 dot, this is instead equal to E over 2 Q bar 1 dot. Okay, so from here it's easy to see that if you consider W0 applied to Q bar 1 dot E lambda, what you end up with is lambda plus 1/2 Q bar 1 dot E lambda, and therefore this can be identified with E lambda plus 1/2. Therefore, the interpretation of Q bar 1 dot as raising lambda operator is correct. And similarly, this is something that you can check, you can do an exercise just to check these identities. Similarly, if you apply W0 to Q1 E lambda, you will end up with the lambda minus 1/2 Q1 E lambda, and therefore this is what I would identify with the state E lambda minus 1/2. Okay, and therefore the statement that Q1 is a lowering operator is correct. Good. In addition, of course, we from the fact that the Q2 and Q bar 2 is this time is trivial, you can apply Q2 and Q bar 2 on the state, and you will immediately realize that Q2 and Q bar 2 simply act trivially on the state. So in addition, we have that Q2 E lambda is equal to 0 and Q bar 2 dot E lambda is equal to 0. Okay, so we can forget, basically this is just to say that we can forget about Q2 and Q bar 2. Okay, so now the Q1, Q bar 1, the small one, there's the big one, whatever you want to consider, this is just question of rescaling, are indeed annihilation and creation operators which satisfy the correct algebra. Therefore, as we did earlier, we can define a Clifford vacuum in order to construct a representation. So representations can be constructed defining a Clifford vacuum that this time has to satisfy this condition. Of course, let me call this lambda 0. The Clifford vacuum is still in some representation of the Poincaré algebra, but in terms of supersymmetry, it has to satisfy this condition. And now, as we did earlier, we start applying Q bar 1 dot to E lambda 0 in order to build up the whole set of states. Okay, so let's do this exercise. As we did before, we can construct a table with the state. This is not spin, but this time this is helicity. And the number of components. Okay, so if we start with this state, we have helicity lambda 0, and the number of components is 1. There is nothing more than that. Now what I can do is to X with the Q1 dot bar over E lambda 0. Remember, I have just shown you that the action of Q bar increases the helicity by 1/2, and the number of components is still 1. Okay, and at this point, this is most I can do. I have to stop because the other possibility is to apply another Q bar 1 dot, and this will be 0 because Q bar 1 dot squared is 0. Okay, so things stop here. As we did earlier, we can compute the dimension of this representation. In this case, we have 1 plus 1, which is 2. Okay. Even in this case, I can give you some relevant examples. Relevant examples. The first example is the case where lambda 0 is equal to 0. Okay, so in this case we have, well, let's go quick. Let's forget about the state. Let me simply list the set of helicities and the number of components. So in this case, the starting point, the helicity is 0. Yeah. And we have a number of components 1, and then we have helicity 1/2 and number of components 1. Okay, so we have a spectrum of helicities, which is 0, 1/2. Okay, this might be not, this is what we call the massless, I should have written it at the beginning. This is what we call the massless chiral multiplet for representation. Okay. I was mentioning the fact that this might be not completely satisfactory because, you know, if we construct a theory which contains only this, let's focus, for instance, on this particular value of helicity, only this set of 0, 1/2 helicities, the theory is not CPT invariant, because if you remember, under parity, helicity changes sign. Therefore, if I want to build up a theory which is a CPT invariant, I have to complete the spectrum of helicities, adding the multiplet which contains the PCT conjugate helicities. So I should add, we should add the CPT conjugate multiplet with helicities equal to -1/2, 0. Therefore, what is convenient to do is to consider the multiplet 0, 1/2 plus -1/2, 0. Okay. In this case, you can complete the spectrum with the helicity and a number of components. In this case, we start with the helicity -1/2, and we have one component. How many states with helicity 0? Now we have 2, because we have one from this representation and one from this representation. And finally, we have 1/2 number of states, 1. Therefore, the dimension, of course, at this point is doubled. So we have 2 plus 2, which is 4. Okay, let me just conclude with the second relevant example, which is the massless graviton multiplet. That corresponds, no, sorry. Before the graviton, we have the gravitino. Let's go in order. Which corresponds to choosing lambda 0 equal to 1. No, sorry, repeat, tired. If this is already 1, so first of all, massless vector multiplet. This corresponds to lambda 0 equal to 1, fine. And of course, if you look at the construction, the helicity in this case will be 1 and, oh my goodness, this is 1/2. So, sorry. The helicity at this point will be 1/2 from here and 1 from here. So the spectrum is 1/2, 1. Remember that we always have to add 1/2. Okay, so this has spectrum 1/2, 1, and then eventually you can add the PCT conjugate, which is -1, -1/2. Okay, let's go in order. Now, we can construct the massless gravitino multiplet. This corresponds to lambda 0 equal to 1. In this case, the spectrum is 1 3/2 plus the CPT conjugate, which is minus 3/2 minus 1. And finally, the massless graviton multiplet, which corresponds to setting lambda 0 equal to 3/2. And this will give you 3/2 2 plus the PCT conjugate, which is minus 2 minus 3/2. Okay. Okay, I think this is it for today.